the slide, and now I have the much better three-dimensional example. I think we have to put this one in. Yeah. Exactly. Okay, I've done this in 3 dimensions, which looks much better, and the polynomials look more difficult. Because if I were to write down the polynomials generating these ellipses, then you as humans could probably see that they are rotations of one another. But if you go to higher dimensions and more variables, it's very unlikely, right? And the question is for example, one guiding question. Yeah, it works perfectly. Here you can see it in 3 dimensions, like how to algebraically verify that they are rotations of one another. Right. And there are some other applications of this problem. So let's start. We have some actions of the orthogonal group in n dimensions, which is just an n by n real matrix, right, which is orthogonal. And this acts on a real vector space. And now we take a look at the space of symmetric tensors over this vector space, which of degree 2D, which is nothing more than just the space of even degree polynomials, right? And we'll call this just V for short, or V2dn, if the numbers are important. And now we want to determine whether 2 of these polynomials or symmetric tensors actually lie in the same orbit. So we rotate their underlying space, and the question is, can they somehow be moved to one another? And one idea to start out with, how to solve this question, would be to look at the invariant ring. So a very bold first idea is find a generating set for the ring of invariants, which is just the coordinate ring of our vector space. So V2dn is a very large vector space, right? And now we take a look at all polynomials on this vector space, which is like a huge set. And I mean, this is a kind of problematic thing, because if you know anything about it, you know that this is a super hard question. And if we actually want to find a generating set of invariant polynomials, like n is incredibly large, right? There are some bounds on it, but it's too difficult and not really feasible. But, I mean, this is maybe a sensible first idea. And how would you actually use such a generating set to separate orbits? Well, let's say we have 2 polynomials or two symmetric tensors, and then their coefficients become the new variables in our larger space. So we take the 2 different sets of coefficients, we plug them into each generator, and if they all evaluate equally on these 2 different symmetric tensors, then they actually lie in the same orbit. This is how you would do it. I mean, it's a very easy computation, except if n is ginormous. So we kind of want to push down our n. So what is the solution? Well, we find a generating set for the rational invariants. And this is a very similar object, but now we're not looking at polynomials. We're looking at rational functions, or fractions of polynomials, which are invariant under the orthogonal group. And this was done in this paper here in 3 dimensions, which is maybe you see some obvious applications here, but I tried to find some general way to find a generating set here in n dimensions. Okay, and now for some definitions to kind of formalize this idea. So if we have some linear action on a vector space, and then the ring of rational invariants is defined as all rational functions, which evaluate equally on orbits. Okay, so far so good. And now, why is this useful? Why do we want understand such a ring? Well, as it turns out, a set of rational functions, so quotients of polynomial, generate this field of rational invariants if and only if they separate general orbits. And again, I think we've heard this notion quite often. Genericity here means that we find a Zariski open set where they generate orbits, meaning in practical application it's almost everything. There might be some special conditions like some hypersurface where it fails. But in the best case, we already know this hypersurface, so we can kind of exclude these cases. All right. So how do we do this? Well, one of the best theorems to find these generating sets for, like these rational generating sets for the field of invariance is to use the Sechardry slice lemma. First of all, we need to define a slice to do this. So again, we have the same setup as before, some linear group action, and now we take some subspace of our large vector space, which we call lambda. And then we take a look at B, which is the stabilizer. So it consists of all elements in our group G, which fix our small subspace. And the subspace is called a slice if 2 conditions hold, which I think very intuitive. So for a general point, meaning again, we find it's a Zariski open of points where it holds, we need to have that G can move this general point into our slice. So geometrically, it just means we have our large vector space, and we have orbits under the orthogonal group in our example, and then our slice needs to actually slice every orbit, right? Or at least a Zariski open of orbits. And then the second condition is that it doesn't slices these orbits too much. So again, a general condition where we need to take a look at the complexified vector space for algebra geometry reasons. We need a algebraically closed field. And then what we want is that for a general point in our slice, if some element in our group, fixes this element in the slice, then it already lies in the stabilizer. Okay, these are the two conditions. So meaning we generically don't have a too large intersection between orbit and slice. All right, and now if this condition holds, so if we have G, V, and lambda is a slice, then we have a very nice isomorphism between the fields of rational invariants, which is kind of easy to see, or like very intuitive at least. So we have this large field of quotients and the small field of quotients, and what we can do is, given some rational function R, we just restrict it to the subspace. Right? I mean, very easy. And now, if you can think about it, we need the conditions to reverse it. If we have some rational functions which is invariant under B, and now we want to kind of find a function which is defined on our whole subspace V, what we can do is we can just take some element from V, and to evaluate it, we move it to the slice. Because by condition 1, we can actually do this. And then we can evaluate it on our R, which is just defined on the slice. Okay, and because we are working with rational function, it's actually not a problem that this just holds on a generic set. Because everything, we can always divide by the set where it doesn't work, and then we're fine. All right, so this is actually what we want to do. And in our case, of the even degree symmetric polynomials, we find a very nice slice. So I'll just do the example for degree 2, because this is easy to see, and it also just encapsulates everything. So in degree 2, we're just looking at the space of quadratic forms, right? And this is nothing else than symmetric matrices, because quadratic forms can always be written as a symmetric matrix, so a coordinate vector, a variable vector times the symmetric matrix times a variable vector. And now our slice are all quadratic forms where we have no mixed terms. So how can we move a generic point onto the slice? Well, we know if we have a symmetric matrix, we can always diagonalize it with an orthogonal matrix, right? And if you think about how the action is defined, acting with this element in the orthogonal group on our quadratic form is just changing coordinates of our symmetric matrix. So we can just have the symmetric matrix corresponding to the quadratic form and then diagonalize it. Okay, and the second condition also holds, but I won't do this. And now to go from this slice to a general slice, we can use the harmonic decomposition of the polynomials, which is basically, we find actually that the space of quadratic forms is always a subspace, in some sense, of the space of degree 2D polynomials. Okay, and now we have this very nice isomorphism, and very importantly, we find that the stabilizer subgroup is a group of sign permutation matrices. Because if you think about it, we have a diagonal matrix, and then we have a coordinate change matrix, which has to fix the property that it is still a diagonal matrix, and those are exactly the sign permutation matrices. All right. And this is a finite group, meaning this is suddenly a much more tractable problem. All right. And now, how do we continue from here? So the main idea here is to find an equivariant basis and kind of reduce the problem even more. What is an equivariant basis? It is a basis where the sign permutation matrices kind of only permute the basis elements of our vector space, of our slice. Because then we have a reasonable way to build invariants out of them, because we know how the action looks like. And the idea here is to use something which looks like a monomial. So we have some very complicated formal definitions, but this is not very important. So if you take a look at monomials, and then you think about the sign permutation matrix acting on these monomials, well, the only thing that it does, it is kind of permutes the indices, and we might get a minus in front, right? So what we do is we take a look at the monomials in our large V, and then we basically equivariantly project them down onto the slice. So what we are getting are not really monomials, but they behave in exactly the same way. And there might be some linear dependence, but this is also not too difficult to understand. And most importantly, we are actually only interested in a very certain set of monomials because everything can be reduced to this set. So we are interested in monomials, which basically are image in base elements, which are image of the form xi, xj to the 2d minus 1. So they don't actually look like this, but they are the image under the projection of these monomials. And now, if you think about it, how do sign permutation matrices act on these monomials? Well, we can swap we got a minus here, minus xj xi to the 2d minus 1. Yeah, this is right. And now, what happens? Well, we can just swap I and j by some permutation. We can get a minus in front. And if we swap I and j, we also get a minus in front. And now, it is sufficient to find invariants of this ring, right? This here. So we take a look at the field generated by all formal variables of the form mij, where I and j are different. And we have that mij is minus mji. Okay, and this is now simple enough that it can be done by hand. And I just show you the set. I mean, it looks very confusing, but there is some sense to it. Because what we can do, now there's a very nice visualization. What we are basically having is we have some graph. 1, 2, 3. The first non-trivial example is n equal to 4 in this case. And we have basically directed edges. And every mij corresponds to an edge. And what our action is doing, it is first of all permuting the vertices of this graph. And secondly, what we can do is we can basically flip all the edges corresponding to one vertex. So if we put a minus at 1, we are flipping all these edges. And now, what we want to do is we want to find a generating set for the invariant. So something, now we are using the Rosenlicht theorem the other way around. We are proving that this set over here is a generating set for the field of invariants, the field of rational invariants, by proving that it separates orbits generically. And what we are doing is, first of all, we are taking PLs and QLs, which very much look like power sums in two different ways. And this helps us to separate the isomorphism of graphs. And as you see, we square everything to not worry about minus ones. And then the very last thing I think is very neat, because these first two sets of polynomials are able to separate up to an open these graph isomorphisms, these changes of graphs. And now we only have to worry about the minus 1. There might be some like forbidden flips in here where we just flip one edge, but not the other ones corresponding to this vertex. So what we are doing is, as you see, we take mij, jk, and ki. So we always take at every possible triangle in here. And now what we see is if we flip the edges corresponding to one vertex, it always cancels out because there are always exactly two edges adjacent to it, meaning this product must be invariant. And this is exactly what filters out the minus ones. And now, if you're familiar with the graph isomorphism problem, you might say, well, I don't think this actually works because like finding out whether two graphs are isomorphic is an incredibly difficult thing, right? And the interesting thing is, now the open condition comes in. Because what I'm doing is only finding an open where this works. So we show that this separates orbits, but only in a Zariski open. And as it turns out, what you might be tempted to do is set mij to 1 if there's an edge between I and j, and otherwise to 0. And then in this way, you can give me two graphs, and I can plug them in and see if they're separated. And the question is, this doesn't work. And this is exactly the Zariski open where it doesn't work, meaning somehow finding out whether two graphs are isomorphic is something very difficult. But if you change the number somewhat and don't have this binary 1 and 0, then we can solve this problem, which is also, again, why the ring of invariant doesn't work. Like separating every orbit in this case is probably super hard. I mean, it's an interesting problem in computer science, but doing it in a generic way actually works. All right. Oh, yeah. Thank you very much. Do you have any questions?
So we have time for some questions. Yes.
Maybe I can just speak very loud.
Yeah.
So can you be a bit more explicit on what is the open set on which it's?
Yes. So yeah, I was a bit vague there. So the idea is that whenever you have like mij, and whenever sums of mijs are equal, it doesn't work. So you have to check every possible sum of mi's and mijs, and they all must be different. Which is because otherwise you could kind of simulate smaller graphs in these bigger graphs and separate them, and this also doesn't work.
Other questions?
Yeah.
Yes.
So the starting question was about even degree polynomials.
Yes.
Right? Why just even degree? What about odd?
Yeah, because this slice here, if you take a look at, if you go back to the slice, this slice here works for only for degree 2, and then we can, like, using the harmonic decomposition, we can kind of extend it to degree 4, 6, and 8. But this slice doesn't work for odd degree, and you need a slightly different slice and different techniques there. Yeah.
Other question? If not, we thank Henri again and go for a break.